Hi to all. In this video, we are going to see about estimation of no load current and leakage reactance. To find or to estimate the no load current and leakage reactance, we should do block rotor test and open circuit test um, of induction machine. Here they are given the um, procedure. Connections are made as shown in the circuit diagram. Okay, keeping the three-phase induction, three-phase auto transformer voltage is 0. uh, Output position, the supply switch S1 is closed. By varying three-phase auto transformer, the rated voltage three-phase induction motor is applied. All the meter readings are to stop the motor. Three-phase auto transformer brought back to initial condition. Okay, in this test, what we are doing, this is a three-phase transformer or auto transformer. We are increasing the voltage gradually and making the motor to run at rated speed. Once it got rated speed, we should measure the that ammeter readings of these two ammeter and voltmeter and two wattmeters. Okay, we are not going to give any load to the motor. That's why it's called no load test. Okay. Second one, block rotor test. Here also the same way we are going to give the connections, but here that drum, the external drum of the motor is tightly uh, tightened by the load. So before starting the motor, it should be in tighten. So when we give the rated current, we are going to measure the voltmeter, ammeter readings. Okay. Connections are made. The brake drum of the induction motor is blocked from rotation by tightening the belt. By keeping the three-phase auto transformer voltage in zero output position, the supply switch is closed. By operating the three-phase auto transformer very slowly, apply such a rated current. Here, for the block rotor test, we should do for rated current. But in the case of open circuit test or to find the value of no load, uh, we are not going to block that one, and we are giving the rated speed of the motor. Okay, no load current as seen in the figure, this one. Okay, no load current of the induction motor has two components: magnetizing component Im and iron loss component Iw. Phase relation between these two currents shown in figure 4. The no load current I naught is equal to square root of Im square plus Iw square amps. Okay, this is the phasor diagrams. Okay, with respect to rotor and with respect to motor. Magnetizing current. The magnetizing current of an induction motor is responsible for producing the required amount of flux in the different parts of the machine. Hence, this current can be calculated from all the magnetic circuit of the machine. The ampere turns for all the magnetic circuit such as stator core, stator teeth, air gap, rotor core and rotor teeth gives the total ampere turns required for the magnetic circuit. The details of the magnetic circuit calculation are studied in the magnetic circuit calculations. Okay, based on the total ampere turns of the magnetic circuit, the magnetizing current can be calculated as magnetizing current Im is equal to P into AT 30 by 1.17 kW T phase, where P number of pairs of poles, AT30 is total ampere turns of the magnetic circuit at 30 degree from the center of the pole. T phase number of stator turns per phase. Iron loss component of current. This component of current is responsible for supplying the iron losses in the magnetic circuit. Hence, this component can be calculated from no load losses and applied voltage. Iron loss components of current Iw is equal to total number of losses divided by 3 into phase voltage. No load power factor. No load power factor of an induction motor is very poor. Okay, if there is no load we are given, that time that power factor value will be very less. As the load on the machine increases, the power factor improves. Okay, when we add the load, the power factor also improve. No load power factor can be calculated knowing the components of no load current. Okay, no load power factor cos phi. No load power factor cos phi is equal to IW divided by I naught. Leakage reactance of polyphase machines. Leakage reactance is equal to 2 pi f into inductance. That is 2 pi f into flux linkage by current. Okay. Note. Useful flux. In the flux that links with both primary and secondary windings. Here is a three-phase induction motor. So stator and rotor. Okay. The another name of three-phase induction machines are rotating transformer, because what transformer having the same type of field, everything the three-phase induction machines also have, because we are not going to give any supply to the secondary. Here we are not going to give any supply to the rotor. It's purely induction based. Transformer also purely induction based. That's why three-phase induction motors are called rotating transformers. So here primary in the sense stator. Okay, useful flux. It is a flux that links with both stator and rotor windings, and it's responsible in transferring the energy, that is the electrical energy into mechanical energy. Okay, the path of the useful flux is the magnetic core. Leakage flux. If the flux that links only with the stator or rotor windings and is responsible in impairing inductance to the windings. The path of the leakage flux depends on the geometrical configurations of the coils and the neighboring iron masses. Okay, thank you.